All right. Good afternoon, everyone, and welcome to the wireless section of the talk. Okay. So my name is Hooman. This is how I used to look like a few years ago. I got my PhD from UCLA in 1999, and I've been in Broadcom since. I also teach at UCLA. I cover circuit and electronic courses over there. My area of expertise is designing circuits, analog, digital, mixed mode for wireless applications. This is what I do at Broadcom all these years. Broadcom at the moment is a $1 trillion company, so we do almost anything in the field of semiconductor design. My business unit, which is WCC, short for wireless communications and connectivity, we design wireless chips for smartphones, tablets, Mac computers, and access points. So for that, I guess that's the reason I've been chosen to give this talk about wireless communication. So I'm going to talk about a bit of history and basics of how wireless communication systems work, what is the purpose. And then as a case study, I'm going to focus on one of the building blocks. Obviously, it's a very vast topic and many different aspects of it. So I've chosen the low noise amplifier, or LNA, as a case study that I'm going to talk about in somewhat more details throughout the presentation. So it all started in 1856 when James Clerk Maxwell published his 4 basic fundamental of electromagnetism, or the basic famous equations, which predicted the existence of electromagnetic waves and the fact that if you have magnetic electric fields, they travel in the air with near the speed of the light. And shortly after, Heinrich Hertz, the famous Hertz that frequency unit is after, not the rental company, he, through a bunch of experiments using big capacitors and spark and light, he managed to experimentally validate the Maxwell equations, the existence of electromagnetic waves. You can see his setup. And more importantly, he was actually able to receive and transmit electromagnetic waves, one end to the other, although he wasn't really transmitting or receiving anything meaningful, but he verified the concept and effectively he built the first radio. And soon after, a number of people started to actually sending and transmitting real useful information. Marconi, which I'm sure name you've heard of, he was one of the pioneers. That's his setup. That's how he did. And by early 1900, about a century or so ago, people were actually be able to receive and transmit wireless transatlantic. The second breakthrough came when the vacuum tubes were invented in early 1900. The vacuum tubes you may or may not have heard of. They are kind of like light bulbs, and the physics are very, very different fundamentally from how the transistors work. But in practice, their modeling and the behavior is very much like a transistor. And one of the pioneers of this era was Edwin Armstrong, which he did very notable contributions to the field of radio design, and particularly there are 2 architectures still in use today. One is called regenerative radio, which at the time you can see the setup, and it was used for wireless telegraphy, sending Morse codes, wireless, sounded like a very important breakthrough. As you can see, the setup is extremely simple. It has only one vacuum tube. That's all it is. Think of it as a transistor and a bunch of passive elements around it, sends to the antenna, and also is capable of receiving. And the second notable contribution of Armstrong is what we call super heterodyne radio, which I'm going to briefly talk about the architecture. And this is how it is. You can see a bunch of amplifiers, a bunch of filters, and a particular block known as mixer. I'm going to justify why this is needed. And also a local oscillator. And this is the radio that he built at the time. You can see these 6 vacuum tubes. Kind of think of it like light bulbs. So you can imagine there's so much you can do with these bulky, fragile, and particularly power-consuming elements, vacuum tubes, essentially acting like transistors. So this took us till mid-1900, and the third breakthrough came when transistor was invented in 1947 in Bell Labs, and shortly after, 1954, TI came up with the first, what they called pocket radio, as you can see a picture of. And this kind of reminds me of nowadays that we carry cell phones in our pockets. Essentially, that's how it was, the equivalent back in 1950s. And you have to also think about the context. This was the height of Cold War. So people were building bomb shelters. They were afraid of an imminent nuclear threat. So having a radio in pocket was more of a necessity as opposed to luxury. And transistor technology has evolved dramatically since. Today, this is mostly dictated by Moore's law and still going on to a bit slower extent, still though happening. And radios today, they consist of tens or hundreds of millions of transistors, as opposed to the TI transistor radio I showed previously, which had only 4 transistors in it. So they're responsible for very complex functions. Shown here is a breakdown of the latest iPhone 16, and there are a number of radios in it. One of the biggest advantages that all the things we do with our phones, such an important part of our lives. When I teach at UCLA, one of the tortures, biggest ones that I make my students subject to is asking them not to use their phones for the 2 hours duration of lecture. I guess that's kind of the torture you're going through most of today. It shows how important it is, and majority of this is achieved by having all these radios in our phones. So if you look at closely into what's inside of the phone, you can see that there are 6, 7, 8 different radios, different used for different aspects of the use we have for the radio. There's your typical 5G radio, several of them, and that's if you want to make a phone call, which is just about the only thing we don't do with our phones these days. You can have your 2 gig or 5 gig wireless LAN radios if you're doing web browsing, Wi-Fi, connected to internet, watching a video. Bluetooth if you're connected to your headset. There's GPS if you're using it for navigation, if you're visiting a new city. NFC stands for near field communication. It's when you're using your Apple Pay or Google Pay for near field communication, ultra wideband, and so many other auxiliary circuitry associated with it. Now the radio spectrum, or RF, radio frequency, what it is strictly speaking, is a portion of the electromagnetic spectrum which spans anywhere from 1 hertz to 3 terahertz, which is shown here. And after that is infrared. A little bit after that is the visible light, ultraviolet, and then the X-ray and the harmful radiation. And if you focus in this part, you can see that most notably and most traditionally, you can recognize the AM, broadcast, amplitude modulation radios, kind of early on, the TI radio, for instance, and frequency was on the order of kilohertz. Also shown is the wavelength associated with the frequency on the top, which is essentially speed of light. That's how electromagnetic waves travel in air, divided by the frequency. And then the FM broadcast is around 100 megahertz. And for the most part, for the applications that I'm personally interested in, and most of the radios I showed you inside your iPhone or your smartphone, they operate in this kind of range of frequency, which is several gigahertz. Notable applications are ISM bands, 2.4 gigahertz, for instance, which is somewhere around here. That's your Wi-Fi frequency, or 5G, and this is 4G, it's a few years old, similar. It ranges from several gigahertz to a few tens of gigahertz. So when I talk about radio frequency or RF or high frequency, this is kind of the frequency that I have in mind. Now, the purpose of a wireless communication system is to take some information, let's say your voice, if you're making a phone call, send it through the air, and receive it on the other end. That would be the person you're talking to. Now, the information is usually centered around 0 in frequency domain. This could be voice, could be image, video, or data, and it ranges from several kilohertz in the case of audio to tens of megahertz in case of data, for instance, if you're web browsing. So this signal, we call it baseband signal. It's rarely, in wireless communication, rarely you will send this baseband signal directly, as is through the air. Several reasons for that. One is, the basic one, is to accommodate multiple users. A good example is FM radio or FM radio stations or TV stations, where you're changing your channel, you're tuning to different frequency. The content is the same information at baseband, but it's transmitted over different frequencies, and you can select which frequency you want by tuning your radio to that channel. Another reason is the size of antenna. I showed you in the previous slide that the wavelength is fairly big at lower frequencies, tens of megahertz or a few kilohertz, whereas at the range of frequency we are doing wireless communication, several gigahertz, the wavelength is on the order of centimeter. So if you look at your iPhone, for instance, you see two rings on the top and bottom. These are the antennas which are on the order of a few centimeters. There is also the better or more effective, more efficient transmission. So for that, we have three portions or three sections, very similar to actually what Kevin showed. We have what we call the transmitter, which takes the baseband information, which is around 0, and ideally doesn't change anything. It just shifts it in frequency to a much higher frequency known as a carrier frequency, or FC. That's the gigahertz range frequency that I discussed earlier. This is now sent through the air. Along the way, it picks up noise and interference because there's so many other people and users also receiving and transmitting information in real time. And the receiver job is to take that signal, which is now a bit contaminated with all the non-idealities, and bring it back to baseband where the signal is. That would be when you're listening to, let's say, your friend that you're talking to. So the very process of upshifting the frequency, the baseband frequency around a carrier, is known as modulation, and that's the key or the number one task that the transmitter is expected to do. The reverse of that happens in receiver. The frequency downshifted or downconverted around the carrier back to the baseband. Now, how this is done in transmitter, if you look at the baseband signal as something like this in frequency domain, centered around 0, what we want to do ideally is to upshift this in frequency. So the carrier signal x underscore c of f would be exactly x of f just shifted by fc, x f minus fc. And from basics of Fourier transform that you know, in time domain, you have to multiply x of t by e to the j 2 pi fct to shift it in frequency by fc, or alternatively, you can see that this is convolved with this in frequency domain, which is spike or impulse at fc, and upshifts the frequency. So this introduces a new block into our system known as a mixer, which does the multiplication as described here. The challenge, though, is that the signal that is multiplying with e to the j 2 pi fc is a complex signal. It's not real. It's not something we can realistically implement. Now, to get around that problem, we recognize the Euler identity, and you see that e to the j 2 pi fc can be broken into cosine plus j and a sine. So rather than one multiplier or mixer, you need two of them. One is driven by cosine, the other one is driven by sine. And these are real signals, and they're known as local oscillator signals. They're basically oscillators that are just 90 degrees out of phase, and you sum them up. Now, still there is a j. It's not enough to just simply add these two. It's I plus j times q. And to get around that, the I and q signals which are fed to the mixers, the x of t, they are x of t one side on the I side, and the q side is 90 degree phase shifted version of x of t, is known as Hilbert transform. 90 degree phase shift is equivalent to multiplying by j in frequency domain. So effectively, you get I shifted, q shifted by sine and cosine. There is a j also built in, and they are added up. So this exactly implements the function we are interested in. This is known as single sideband transmitter, and is the basis of all the modern transmitters in use today. So as an example, this is how a modern transceiver looks. Even though at the time, at a given point of time, you're transmitting and somebody else, somewhere else is receiving, most practical radios are both include transmitters and receivers because of the problem of duplexing or two-way communication. You listen and you talk on the same device. So shown here in the middle, you can immediately recognize the single sideband transmission, I and Q mixers driven by a local oscillator 90 degrees apart. The baseband information at x of t and I and Q versions of x of t that we now need, they are done all in digital domain. There's a very sophisticated digital engine known as physical layer and MAC that produces that. This is fed into a data converter, which by this point you're very familiar with. It's filtered, cleaned up a bit, and that's what's fed to the input of the mixer. Then you get I plus JQ up conversion. And eventually it's amplified by a block known as a power amplifiers, because you have to put a strong signal which is capable of traveling many meters or miles even to the other side, which would be the receiver. Now on the receiver you do exactly the opposite. You're dealing with a small signal, hence you have to amplify it immediately. That's the block LNA, which we'll talk in more details. You do the single sideband down conversion now. By a similar local oscillator, it could be the same, could be a different one, depending on application. You filter that, and now you digitize it, and then all the processing is done subsequently in digital domain. This is typically known as SoC, or System on a Chip, which has all of these functions integrated into a single die. As an example, I picked what I would consider the state-of-the-art transceiver or radio. It happens to be the company that I work for, no bias. And you can see it's a fairly complicated chip, and you can see about 2/3 of it is all the digital engine, Phi and Mac, and then on the left side you have the radios. It integrates multiple radios. There are 2x2, 2 gig and 5 gig wireless LAN radios. 2x2 means MIMO. It means that you have 2 replicas of your receiver and transmitter for better reception, for better quality, for better throughput. You can operate concurrently between 2G, 5G, and Bluetooth, so these are all independent radios. All of them are integrated into a single die. So with the background, I'm going to just now focus a bit more on what would be our case study, the low noise amplifiers and the circuit of that. So imagine you have a power amplifier and a transmitter signal. It produces a near ideal signal. Let's assume that's the case. This goes on the antenna and is transmitted over a long distance. And by the time it gets to the receiver, it's attenuated. It's not just a physical distance. You have things like your signal could be blocked by some obstacle. There could be reflection, could be various reasons that by the time the signal hits the receiver antenna, it's pretty weak. So also it's going to be accompanied by noise, which I'm going to talk about in a bit more details, but you have heard of it in the previous talks as well. So what you have at the receiver input, effectively you have a source which has a small signal accompanied by noise, which is usually modeled by a resistor attached to that source. And if you look at this in the log domain, the ratio of the signal power to the noise power is known as SNR, or signal to noise ratio. Why SNRI? Because that's what coming at the LNA input. I stands for the input. Now you can see that it's pretty logical that right away you want to amplify this small signal that has come to the receiver input. Hence, you use a low noise amplifier, which is at heart an amplifier, but not any amplifier. You also want it to be low noise. And the reason for that is that once this is amplified, the signal and noise are amplified by same equal amount. The LNA, it's a linear circuit, cannot distinguish whether it's noise or signal. They both increase in level. So the signal to noise ratio is maintained. It's not going to improve. At best, you can maintain that. The problem, though, is that LNA uses active circuitry, so adds its own noise. So what you get is really the noise is going to be even lifted further. And as a result, the final output signal to noise ratio, which is this level compared to that level, is going to be degraded by how much that amplifier is adding its own noise. And the amount of degradation is, in the log domain, is quantified as noise figure, which is a key figure of merit for LNA and your receiver. So in order to understand or have a better understanding of the noise and the low noise amplifier, I'm going to spend the next 10-15 minutes or so on giving you a preview or a brief description of how noise is generated, how it's treated in circuit. Usually this topic we teach in graduate level, so I understand many of you may not have seen it. So imagine you pick a resistor at random, 1 kilo ohm resistor, and look at its open terminal outputs. Measure this voltage V of t. What you're going to see is a waveform kind of like this, which looks like consists of a lot of random fluctuations. Now, if you pick a second resistor, the same resistance, the same measurement setup, you will see another waveform which kind of looks the same, all the fluctuations and randomness, but it's entirely different. This type of signal, in this case, which is representing the noise of resistor, is known as a stochastic process, or simply put, a random signal. What it is for a given sample, let's say any one of these, it's a time function. Whereas if you freeze the time, let's say at t0, and collect all the voltages of all your samples belonging to that time, this will constitute a random variable. And for that reason, it must be treated as such. You have to resort to statistical means to characterize that, like probability density distribution function, usually Gaussian in electrical random signals, expected value or average mean, and other properties. Now, it is very convenient to deal with our signals in frequency domain. If you have a deterministic signal, you can simply apply Fourier transform and do a lot of analysis in frequency domain, something we all do always. The problem with this is it's quite meaningless to apply Fourier transform to any of these signals, which are random in nature. There is a key property, however, of these random signals, including noise, is known as stationary, which in strict sense, what it means is that the property, while the voltage itself is a function of time, the statistical properties are not time dependent. And in wide sense, what it means is that the expected value or statistical average is a constant. You collect a whole bunch of samples at t0, take the average, that will be equal to t1 collection and taking average. And secondly, the autocorrelation, which is the expected value of the voltage at some point t times at some point t0. Remember, each of these are random variables. That's a deterministic signal, only a function of time difference. A single variable, I call it tau. So since this is deterministic, the statistical properties don't change, we apply Fourier transform on this, and that is known as power spectral density. So majority of my talk, I will deal with power spectral density to deal with noise, which is essentially the Fourier transform of the autocorrelation. Now, if you pass this through a system, what you have to look at is the spectral density of the output, which can be proven to be equal to spectral density of input times your transfer function magnitude squared, which is somewhat different from the deterministic signals that you've seen earlier. So where is the noise originated? In the case of resistor, it's what we call a thermal noise. What it is the electrons in the resistor, as long as temperature is higher than 0 Kelvin, they gain some energy from outside, and they're going through some random fluctuations. That randomness is what causes that voltage across the resistor, even though there is no source associated with it. That randomness, movement of electrons, is really the source. This was predicted by Einstein in 1905, and later on Nyquist formulated this. The power spectral density turned out to be roughly a constant. It changes with frequency a bit, but for the most part, it's frequency independent. It's a function of K, Boltzmann constant, T, temperature. Certainly, that's where the randomness and all agitation comes from. Of course, linearly proportional with the resistor. If you take an integration over a certain bandwidth, let's say 1 hertz, you can convert this from energy to power. So we can use these interchangeably to characterize the noise. So for that, you can model the resistor with ideal resistor now, along with a voltage source whose spectral density is given by this. And now if you look at these open terminal voltages, you're going to see the impact of noise here. You can use the Norton equivalent. And similarly for transistor MOSFET in inversion, the channel consists of electrons which also gain energy, and they fluctuate in a random fashion. So your actual drain current consists of what it is, along with the randomness aspect of it, which is modeled by this. Gamma is a constant. It's process dependent, something around 1. Gm is the transconductance. And lastly, the reactive components, L's and C's, are noiseless. So with that background, now let's try to do some manipulation. If you have a complicated circuit consisting of many transistors and whatnot, and resistors, it is foreseeable that you can lump or model all the noise sources as one equivalent voltage noise source and one equivalent current noise source. I'm using these funny shapes, the plus minuses or arrows for voltage or current source not shown because it's not important. For noise, it's always squared when you do the power spectral density. So -1 versus +1 doesn't make any material difference. You can think of it like a Thevenin equivalent source. No matter how many voltage current sources you have here, you can bring one voltage source, open circuit, or one short circuit source. I think Ali mentioned it in the morning. In the case of noise, you need both of them for any termination. So a typical system would be a 2-port, which is noiseless now. Its noise is captured all at the input with these sources, along with a source, which is, for instance, the transmitter antenna output. And this source has a resistance, which itself contributes to the noise. So let's revisit now the noise figure definition. The noise factor is, in linear fashion, the ratio of signal-to-noise ratios. And if you take 10 log of that, that will give you noise figure, which you saw earlier. The ratio of the signals is basically the gain, G. And this could be less than 1. Doesn't have to be always an amplifier. So you have the noise total at the output, normalized by gain, normalized by the noise at the input, which is coming from your source, which is incoming to the amplifier. And you can divide it by G, the noise at the output. That's the total noise at the input, which belongs part of it to amplifier, part of it to the source, normalized to the source. Clearly, this is greater than 1. You can never improve signal-to-noise ratio. Now, to do a bit more math, we can look at the Thevenin equivalent of this circuit. For noise calculations, the signals don't come into the picture. You just want to find the ratio of total input noise versus the source noise. So we short this out, and this would be the Thevenin equivalent of the amplifier, Vn and In. And from this, you can see that the noise factor, according to this definition, would be the noise spectral density to the source. That's your Ni. Whatever the amplifier is adding, which is this Thevenin equivalent all squared up, that's your Nia. Normalized back to your Ni. This is clearly greater than 1. Only in the absence of any noise of amplifier, this approaches 1. That's where the signal-to-noise ratio is maintained. In practice, it's usually degraded. We also see a dependence to the source impedance. There is a ZS and RS, which is the real part of the source impedance. That's what causes the thermal noise of the source. That inspires us to do perhaps some optimization. For the moment, if you take your noise figure equation and just replace your source with just a simple resistive version of it, RS is representing that, you can see that for a small value of RS, this goes up to infinity because of this in the denominator. For a very large value of RS, because of the square dependence in numerator, it also shoots up to infinity. And you can see that it's conceivable that there is somewhere in the middle that you can find an optimum RS that gives you the minimum noise figure. And for more general case of ZS, a complex source as opposed to RS, you can take partial derivative of this versus real and imaginary parts and set them equal to 0 and pray that that's a minimum, not a maximum, which is a minimum. And from that, you can find your optimum source impedance, which gives you the best noise figure. Designing amplifiers, a lot of it involves with this type of optimization. But then you may say, well, wait a minute, is source something we can actually change? Isn't that the signal generator or the transmitter which is driving the receiver? It's not in our control to change it, and that's true, except for we can always insert what we call a matching network between the noisy 2-port and the actual source, let's say 50 ohm source, which will transform the impedance to something of our liking, in this case the optimum, ZS. And since this network is lossless and reciprocal, it is not going to change the available power here. The power gain is 1, it's lossless. It's not going to also change noise, already established. L's and C's, lossless elements, are noiseless. So the signal-to-noise ratio is intact, as if you're getting the same thing here as used to right at the source, whereas the impedance is transformed to what we like. So to summarize, we have a source, let's say typically 50 ohm, we can transform the source impedance through a reciprocal and lossless matching network, and then you have your noisy two-port, which can be modeled with the equivalent noise sources. Looking into two-port, you see some input impedance Z in. Now, oftentimes, this matching network now belongs as a part of your overall two-port, let's say the amplifier that we're interested to design. Oftentimes, it's desirable to see a fairly well-defined impedance looking into the amplifier, usually 50 ohm. For that to happen, given that this network is lossless and reciprocal, then Zs must be equal to Z in conjugate on the other side on this side of the matching network. This is known as conjugate matching. On the other hand, we just saw that to get the best noise performance, you would like your Zs to satisfy some Zs optimum, came from the noise figure equation and taking the derivatives of that. And there is no reason in the world for these two values to be the same. One is Z in is coming from physicals, R's and C's associated with your amplifier. The other one is purely driven by noise, the Vn and In and all noise sources. And that's the most challenging aspect of the LNA design that I'm going to go through in the remainder of the talk. One idea, one remedy for this would be to employ feedback. The feedback must be lossless because we don't want to deteriorate the noise property of the amplifier beyond what it is already. Well, we know from feedback theory that the impedances, the input-output impedances, can be changed according to the type of feedback you employ. This is the topic that I'm going to focus on in the remaining 10-15 minutes of my presentation. So what are the LNA requirements with that noise background? It has to be an amplifier, obviously, but there are also additional requirements. It must have a well-defined input impedance. I already mentioned that, let's say 50 ohm. Certainly, we want it to be low noise, not to degrade the SNR beyond the minimum possible. And also, it must operate at reasonably high frequencies, let's say a few gigahertz. That's the range of most of the applications that we're interested in. And there's one last requirement that I'm going to focus on. It's not really a hard requirement. It's something made up by me. It should be also simple. Majority of RF circuits, LNAs, mixers, oscillators that I haven't talked about, they are all consisting of one or two simple transistors. Simplicity is important, and you can get more than 2 or 3 RF designers that would agree with me that it's a key part of the radio design. So if I ask you, what is the simplest amplifier that you have ever seen, maybe that would be a good starting point to satisfy the last requirement. What is the simplest amplifier that you can name? Common source, common emitter. The answer would be the one that you taught me first, probably. That's how it is. It's very simple. One transistor, one load, just an input, gate, the output drain, and a common, which is source. Now, what about the other requirements? It does the amplification. The gain is GM times R, L. We know that. Does it work well at high frequencies? For that, we have to attach all the transistors associated with transistor. And there are 3 of them, one from gate to input, one between input and output, CGD, one at the output, which is everything, the junction, load, and everything else, CL. Now, this will degrade the frequency response of the amplifier. CG particularly is problematic. You see small swing here, fairly large swing here because of the amplification. So this lopsided swing on 2 terminals of CGD exacerbates what you see, or the impact you see at the input, known as Miller effect. It also, at high frequency, makes the amplifier non-unilateral. You'd like your amplifier to be unilateral. CGD will break that. The output capacitance CL, along with the load that you want to maximize to achieve the best gain that you can, will also give you a low-pass roll-off. You saw that in the examples of wireline building blocks. So those must be avoided, or somehow, without causing too much complexity, has to be fixed. And the remedy to CGD is to use a cascode transistors. You have seen this in your analog electronic courses. This added 1 level of isolation from this point to the output. Makes the amplifier again unilateral, or kills the gain from here to there, causes fairly uniform swing on CGD. And at the output, instead of putting a resistor, you can put a tune circuit. this L will resonate with CL at the frequency of interest and around it. And remember that the applications we are interested in are usually narrow band. So this effectively at resonance will look like a resistor. And for practical values of L's and C's and everything else, these are comparable. So with all that, I'm going to, throughout the talk, reuse this equivalent model, which has a CGS. We are yet to do something about it. But the output is effectively the resonance resistance coming from the LC, and CGD is thrown out because we know it's not too important. What about the input impedance? We want it to be well defined at 50 ohm. As it stands, looking into this input, you see a big capacitor. That's all you see, no resistive part. To fix that, we may suggest, well, put physically a resistor here and make these resistors equal to 50 ohm. You get your matching. The problem is this resistor will contribute noise. It's not lossless. And we can do a noise analysis. We can include the noise of the input and the noise of now this matching resistor. They are equal resistors. Their spectral densities are the same. You just see a simple voltage divider by factor 1/2. And you can see that if you use superposition, they contribute equally. So as it stands with everything else ideal, this will suffer from noise factor of 2 or noise figure of 3 dB, which is usually unacceptable in almost all applications. So now this, we can think of what I mentioned earlier. Can feedback be utilized to do something, to fix our input impedance and yet not degrade the noise much? And my second question for you would be, what is the simplest feedback that you have seen that might be suitable to add to our common source amplifier? Yes?
Like a unity gain feedback?
Sure. It's something much simpler. Degeneration. You may not see it as a feedback. In fact, the degeneration is usually taught in analog courses before even the feedback is taught. It's so simple. I can prove it to you why it is a feedback. You can see that the output current is coming through the drain, coming back through the source, goes through this resistor, degeneration impedance, let's call it. In the absence of it, the input is same as VGS transistor input times GM is the output current. Once the degeneration is put back, your VGS is now V in. Subtracted from that is the current at the output sensed by this impedance creates a voltage Z times IO, and that's your VGS now times GM is your new output current. So in a way, this circuitry is sensing a current at the output, is returning a voltage at the input. It's a series or current voltage feedback. So the next question is, what about the choice of Z, the feedback element? What you'd see in your analog courses is a resistive degeneration. But this turns out to be almost or nearly as bad as putting the resistor here. This will add its own noise, and it does give you a real part, unlike the original case. But in terms of noise performance, it's as bad as putting the resistor here as opposed to there. They both contribute equal noises with respect to the source, or 3 dB or more noise. But this is not surprising, because we talked about noiseless or lossless feedback. Resistors are not noiseless. So that leaves us with two choices. Either this has to be an inductor or has to be a capacitor. And what we are doing here is we are sensing a current, returning a voltage. In the case of capacitor, the voltage is 90 degrees behind the current. In the case of inductor, the second choice, the voltage is 90 degrees ahead. So there is a net 180 degree difference. This means that one leads to positive feedback, that's the capacitor. The other leads to negative feedback. In the case of capacitor, this is your CGS. That would be your degeneration. You need to provide a current source or something to let the current flow or provide a DC path for the current. Looking into this node, you see that your input impedance has a real part, certainly, because of feedback, but that's negative. So if you put an inductor here, you create a resonance tank, and this is an oscillator, what is called a Colpitts oscillator, which would be probably the subject for next year Circuit Insight talk, maybe, the oscillators in general. I think I disappointed someone who was looking for oscillators because that's the only thing that I'm going to mention about oscillators. But the last choice we have, the inductor, that works, gives us a positive, negative feedback. There is no worry about the DC path or DC current generation. And I will show you in a minute that this does indeed give us a real part of input impedance. And that real part is positive, meaning that the feedback is negative. I have about 10 minutes, right?
10 minutes for Q&A. Almost done.
Oh, almost. Okay, so I'll wrap it up. So let's look at the input impedance and verify that it's resistive. So what I have is the original circuit. I put the small signal equivalent. This is the output current. I convert this to a Thevenin voltage source that's shown here. This clearly shows the feedback. This is the feedback factor. This is the feedback loading. So the input impedance in the presence of feedback is the open loop input impedance, which is CGS in series with L, times 1 plus loop gain. The loop gain is feedback factor, is just the impedance, JL omega. And then the transconductance gain of an amplifier, you have voltage divider between CGS and L. In the absence of this, that times GM. This indeed gives you a resistive part and some reactive part that must be eventually canceled out. And for that, we add another inductor, usually to resonate with everything left, which is typically capacitive. So that would be the complete circuit. The input impedance will be given as this. And this has to be set equal to 0. This has to be set equal to your 50 ohm. And that's your matching. And lastly, we can look at the noise of the amplifier. For that, again, we can add all the noise sources, the source and the transistor. We satisfy the matching, meaning that this is equal to 0. This is equal to 50 ohm. We can write a KVL here. We can write a KCL here. We can simplify the fact that there is a resonance. I leave it up to you to follow the math. And you can see that the total noise current is given by this. The transfer function is given by this. And the total noise factor is given by this, which can be arbitrarily lowered by playing with L. CGS omega is, of course, fixed. In a way, this degeneration lossless feedback is giving us a noiseless resistor, as opposed to brute force putting a 50 ohm there. Now, finally, this is the general or final circuit of the LNA. We have the cascode, we have the resonance, we have degeneration. The matching could be a bit more complicated than a single inductor. The noise factor is given here. Now, of course, L cannot be arbitrarily lowered because ultimately it has to give you the matching. So this is shown here. I've also shown a sample of dual gate layout to minimize the parasitic capacitance, which again, I leave it up to you. And to conclusion, I talked about wireless systems and circuits. They are inseparable parts of our lives. We can't live without them. Everything we do nowadays is thanks to them. They consist of mixers, amplifiers, and filters, and a whole lot of them. As a case study, I showed you a circuit of low noise amplifier, which oftentimes, and in this example that I showed you, is designed by incorporating lossless feedback, and you can achieve good sub 2 dB noise figure out of your circuit of LNA. So that's my talk. Thank you.